Alright, here's one of my favorite topics. Usually students don't have quite the same enthusiasm I have for this, but maybe you'll be different this year. The polyatomic ions are one thing that students have to go through in chemistry that they complain a lot about. The traditional approach to this is to simply give you a list of ions and say memorize it. Well, I'm giving you the same ultimatum this year. There are certain polyatomic ions that you need to memorize, and you probably already have this list. What I'm hoping to do with this brief discussion is to give you more of a reason of why the polyatomic ions are named the way they are, hopefully to get some better sense of organization, so maybe you won't think it's quite as random as those lists make them look. There is a method, there is a naming system. Now, for full disclosure, I came up with this on my own, so I don't promise that any of this stuff is exactly correct. But we're going to go through it anyway. You may want to have a periodic table handy sitting next to you as we go through this so you can refer to it quickly. So why don't you hit pause and grab that if you don't have one. What is a polyatomic ion? Well, poly means many, atomic means atom, so we're talking about ions made up of two or more atoms. Most of our polyatomic ions are going to have oxygen in them, so they're going to be called oxyanions. I actually prefer the name oxyanions as we get into this discussion later in the rest of the year. I like oxyanions better. These polyatomic ions are going to be created, formed, made through covalent bonding. So there is sharing going on. Once they are made, however, they are from this point forward going to behave and participate in ionic bonds. So let's think about that. They are made through covalent, and then once they are made, they form these nice discrete particles now that no longer will change. They are going to instead ionically bond with a cation somewhere to form an ionic bond. Now, most of these polyatomic ions are going to have a negative charge because they are covalently created. That involves nonmetals and metalloids, and those atoms typically want to gain electrons, and so overall we will see a preponderance of negative charges almost exclusively. Alright, so here's the naming system. For polyatomic ions, there's always going to be a root name. And that root name is going to come from the other element, if you will, that's not oxygen. We'll call it the least electronegative element. Now remember, for electronegativity, fluorine is the most electronegative, and electronegativity decreases as you go left, it decreases as you go down. So fluorine's at the top of the pile. So the root comes from the least electronegative element in the polyatomic ion. So for example, SO42 is going to have the root of sulf. And then for ClO3, that is going to have the root of chlor for chlorine. There will be a suffix added to the root. In polyatomic ions, there are 3 suffixes. I'll go ahead and tell you first of all that there are a couple that will end in "ide." They are aberrations. So we're not going to discuss why. We're just going to learn those 2. Otherwise, the rest of them will either have the suffix "ate" and "ite." And if you've looked at your list prior to this of polyatomic ions, it looks kind of random. Like let's just throw an "ite," let's just throw an "ate." Sometimes they do, sometimes they don't. Well, it's not that random. The "ate" suffix actually tells you a little information. It tells you that the root element has its maximum oxidation number. So it's the most positive that you could possibly be for that element. "I" then tells me that the oxidation number is specifically 2 less than max. Because if you look again at your list, your "ites" are always going to be 1 oxygen less than your "ates, and oxygen carries with it a -2, so you're going to have a change of 2 in your oxidation number. So there will always be a root, there will always be a suffix. Sometimes there will be a prefix. When there are prefixes, those prefixes will tell you very specific information about the root element. So here are some examples. If you see the prefix per, that means the root element has a +7 oxidation number. Only a few elements can do that. Only the halogens with their 7 valence can be +7, or a few of the transition metals such as manganese with its 2s and its 5d electrons can give you a +7. Then hypo. Hypo is specifically for a +1 oxidation number and really only refers to, again, the halogens. Nothing else really gets a +1 or a hypo prefix, as in hypochlorite, which is the active ingredient in bleach. Sometimes bi is a prefix. Now don't think this bi means 2. I know bi means 2 in a lot of things. But in the nomenclature system of chemistry, bi means that it's a synonym for hydrogen. So for example, if we have HCO3 minus 1, that is properly called hydrogen carbonate. Writing out hydrogen can be somewhat of a pain in the neck, so the prefix bi will shorten that. So instead of hydrogen carbonate, it'll come out to be just bicarbonate. And I'm sure you've heard of bicarbonate as in sodium bicarbonate, which is baking soda. Thio is another common prefix. Whenever you see thio, that tells you that there is sulfur in the compound. And specifically, a sulfur atom has replaced the oxygen, or one of the oxygens, in the polyatomic ion. And then there are some that we're just going to have to memorize. So I put this in here. Okay, so in here, I've put a review of oxidation numbers. There they are. So here's the rules for oxidation numbers. I'm not going to go through these for this lesson. Please refer back to previous lessons on oxidation numbers. And then if you've done that, just read these. Maybe that'll give you enough to go on. But let's move on for the purposes of this lesson. So the oxidation numbers are important to our naming system. We talked about how the prefixes and suffixes do refer to those oxidation numbers. You have to be able to determine the oxidation number for an atom in a polyatomic ion. That's how you're going to decide what suffix, what prefix to use. 99% of the time, oxygen will be -2. As the second most electronegative element on the periodic table, oxygen is very frequently what I call the boss, and it gets to be its ideal oxidation number, which is gaining 2 electrons to complete its octet and be -2. The maximum oxidation number that I refer to is when all valence electrons are removed. So that's the most positive you can be. And here's an example. For SO4 minus 2, sulfur is the atom in question. Sulfur has 6 valence. Now know that from the periodic table. In this ion, sulfur has an oxidation number of +6. So that is maximum. Hence, this is sulfate. 6 valence, that means you can be +6. And then to find the oxidation number, it's going to take a little algebra. Again, please review your lesson on that. Here's a periodic table. If you haven't, you got yours out and you want to talk about it or write some stuff on here, I just want to go through and make sure you understand how I'm getting this maximum oxidation number and stuff like that. Well, for each of the main groups, so we're not really talking about the transition elements, but the main group, we have 1 valence, 2 valence, 3 valence, 4, 5, 6, 7, and 8 valence. And most of you already know that in the group 1 over here with 1 valence, everything is going to be +1 charge. And if the alkaline earth metals, everything is going to be +2. Because you lose those 2 to go down to the previous energy level, you're not going to gain. And then as we get over to the P block, though, with 3 valence, it's still quicker to lose. Now, once we get to 4, something strange happens. Now it becomes, if you will, equal distance to 8 as to 0. So you can either lose 4 or gain 4. The determining factor now becomes which one is easier, and it's a size question. It goes back to Coulomb's law. For the tiny ones, like carbon and silicon, they can be -4. They tend to do that more often. And then the bigger ones are always going to be positive, the metals, lead and tin, and so forth. But the maximum oxidation number for this column is going to be +4. And it can happen, like carbon in carbon dioxide is +4. That's what makes carbon dioxide so stable. And then for the nitrogen column, its maximum can be +5. And then we know that it wants to be -3. So really, an element in the nitrogen group can be anywhere from +5 to -3. That's maximum to minimum. And then if it's going to be like nitrate, then it would have the +5. And then for the oxygen group, its maximum would be +6, and its minimum would be -2. So that's kind of its range now. And for the halogens, it's +7 to -1. And that's kind of its range, maximum to minimum. And again, this is only good for oxidation numbers. These aren't real charges like in ionic bonding. So then we talk about the charge of polyatomic ions. Well, the charge of polyatomic ions is easier than you think, because the charge on the polyatomic most of the time matches what the root element would be if it were by itself. So here's an example I have on the screen of the chlorine ions. First of all, we have chloride, which is monatomic with just Cl, and it's -1. And then you can see that all of the subsequent polyatomic ions of chlorine are also going to be -1. And you'll see that sulfur does the same thing, phosphorus does the same thing, selenium, bromine, iodine. Any element, any root element on row 3 or below, that's the silicon, phosphorus, sulfur, that row, anything on that row or below, it will be this way, and that makes it pretty easy. So here's how you find how many atoms. Given the name phosphate, for example, I know this ion will have a P and an O in it, but I don't have any oxygens, so it will have the generic formula POX. P has, from the periodic table, look at your periodic table, find phosphorus. It's in the nitrogen group. It has 5 valence electrons. There. It's in the fifth, or group 5A, the 5th P group, so I know that it's going to be -3. So automatically I can adjust my charge on phosphate. Again, row 2, row 3 or below, it's going to have the same charge as its monatomic. So POX -3. Now that 8 suffix tells me that P will have a maximum oxidation number. For phosphorus in the 5th column of the P group, group 5A, that's what I meant to say. This is going to be a +5 as maximum. Again, that's 5A. I think I said the 5th group of the P's. I meant to say the 3rd group of the P's. Oxygen is always -2. So if we apply our algebra to this, I have a +5 for the P, and I know that each oxygen is going to be -2, and they have to add up to equal -3. I can solve for that X and get phosphate equaling PO4 -3. And that algebra would set up as 5 plus X times the -2 for oxygen equals -3. Again, X would be 4 there. And you can do this for any element on row 3 or below, and it works perfectly fine. One other thing that you might find pretty helpful to help you remember all of the names is limit the ones you memorize and understand that every element in the same group is going to have the same pattern of naming. For example, on the screen here, I've shown you two halogens. And I start again with the one on row 3, chlorine, because those behave normally. Anything row 3 and below behaves normally. Chlorine follows the pattern of chloride, perchlorate, chlorate, chlorite, and hypochlorite, with the oxidation numbers being -1, +7, +5, +3, +1. Bromine is going to have the same pattern. Bromine is going to be bromide, perbromate, bromate, bromite, hypobromite, with the same pattern of -1, +7, +5, +3, and +1. So in the red, the question is, what do you think the ions will look like? Iodine's ions will look like. Well, I know what they'll look like. They're going to be the same pattern. Iodide will be that. Periodate will be that. And I know even hypoiodite will be IO, -1. They'll be the same pattern. Likewise, I can apply that. If I know that sulfate is SO4 -2, then I know then that selenate will be SeO4 -2 because they are in the same group. And then finally, we end on a down note. Sometimes our rules just don't work. These are for various reasons. Nitrates is an exception because it's on row 2. It's so small that it has some limitations. And its exception is that it's -1 charge instead of -3, like phosphate would be, or arsenate or anything like that. So you just got to know nitrate. Very, very common, very important. Hydroxide's weirdo because it ends in IDE. Cyanide's the other one. I mentioned those, or alluded to those very early. Ammonium's a weirdo because it's positive, but you need to know it because it is very important in acid-base chemistry. Acetate's a weird one. Well, look at it. Acetate has a very low oxidation number for carbon, and it's weird because it's organic. It's actually an organic ion. Oxalate is weird because carbon's +3, not +4. So why does it get to 8? I don't know. Can't answer that. Permanganate is weird because it's a -1 charge overall. Kind of weird, not totally weird because it kind of matches the halogens where you have, like, for example, perchlorate is ClO4 -1. So it follows the same pattern as the halogens. And then peroxide, because oxygen in that case is -1 instead of -2. One of the rare times oxygen is not -2. So you just need to know these. And on this list, these are all important. All right, so that's just an overview. Hopefully that will help. Try to do things like try to figure out arsenate. Try to figure out tellurate. Try to figure out chromate, and bring them to me, and I'll see how well you did at predicting the names of those ions.